First things first, when we talk about parent functions and transformations, you'll remember from Algebra 2 that there are 8 basic parent functions, and I've listed them here. There's the line in the function y equals x, a parabola, which is x squared, a parabola with one arm bent down, which is whenever the power is cubed rather than, odd rather than even. There's y equals the root of x, and the left-hand side is dotted in because if it's an even root, like the square root or fourth root, then only the left-hand side exists, and if it's an odd root, then you get that left-hand side back in there. Y equals the absolute value of x. Absolute value has the effect of just bending the lower part of a line up. Y equals 1 over x. X is 0 is an asymptote. Whenever x equals 0 is an asymptote, which means that you're never going to get out of the range. You're never going to get a 0 on y. So you have 2 asymptotes for y equals x, 1 horizontal, 1 vertical. And then the last 2 I put on the same graph because they're inverses of each other. Remember, the log function and the exponential function reflect over the line y equals x. So these are the 8 fundamental graphs. You should commit these to memory and be able to work with them without any hesitation. Your textbook adds an additional, though obvious, which is that the constant function y equals some constant c, which is a horizontal line through c on the y-axis, and the greatest integer function, which definitely deserves a little bit more explanation. It's technically the greatest integer function defined as the greatest integer less than or equal to x. So we're really talking about a round down function. The function is written this way. You get this kind of double bar for x on both sides, and that's the indication you're talking about the greatest integer. And what that means is for any value you choose, you want the output needs to be the greatest integer less than or equal to x. So if I were to put in a 1 for x, the greatest integer less than or equal to x would certainly be a 1. But if I were to put in 1.5, let's make it a bit bigger, 1.5, well, I have to ask, what is the biggest integer less than or equal to 1.5? It's a round down, right? So it rounds down to 1 as my output. As soon as I get to 2, though, now 2 is the greatest integer less than or equal to 2, because it's equal to. So all the way along from 1 until just to the left of 2, I'm going to get a round down to 1. So it's open. It's open at 2 because 2 now becomes equal to 2. And then all the way like this until I get to 3, right, till the integer 3. So it really is just round to the next lowest for the output. If I'm on the negatives, I would have, well, the smallest integer less than or equal to at 1, it's going to be open, and then go to 0. My intervals aren't very pretty here. And then for negative 1, ask yourself, well, what is the lowest, or better said, the round down at negative 1? So this would be negative 1. And it just continues in this very same fashion, where this value is 2. So it can be a little bit hard sometimes to conceive of the function when we say the greatest integer. But what we really mean is if you rounded down to the next lowest integer for any input, what would the output be? All right, so we remember from Algebra 2 that I can write any function in the form of a times whatever the f of x minus h plus k is. So really all this is I'm taking the y equals the f of x and I'm inserting an a, an h, and a k. So it just spreads out, and then you just have to ask yourself, what is the position in the function what number holds the position of A, the position of H, and the position of K. And then we can translate the graph or produce a transformation on this graph using these inputs. So remember, A provides a squeeze, or Q-U-E-E-Z-E, squeeze or stretch on the function. H tells us to move back and forth on the x-axis, and X is cattywampus, I like to say, because if this is a negative, so if your function has a result of x minus h, then you're going to go forward on the x-axis in the positive direction. And if you have something of the form of x plus h, you're going to move backward or in the negative direction. So X is cattywampus by sign. And then K just says to move up or down, and K is straightforward. You move up or down K units on the y-axis. So let's do a quick example, and we like, of course, y equals x squared for these. So if I have a function y equals 3x minus 2 squared plus 8. So what I have here is I have the squared function. So my f of x is x squared. In this case, see, x squared. And then my translation function looks like this. I've got 3, negative 2, and 8. So what does that tell me to do to the parent? First, let me graph the parent, just so we know what we're looking at. And remember, one characteristic of the parent is it goes through 1, 1, and then it goes through whatever else is happening at negative 1. So in this case, we're looking at the point 1, 1 and 1, negative 1. Negative 1, 1. I don't want to write those points in because I don't want to get too cluttered on the graph. So now, let's look and see what happens when we squeeze and stretch it. First thing I want to do is use my squeeze stretch, or my y equals 3. And the logic behind this is, if I only had 3 in the function, so if I were looking at y equals 3 times x squared, which means all I had was a squeeze or stretch, what would the effect be on the original? Well, I'm asking, what would the effect be on all the points of the graph, particularly 1, 1, negative 1, 1, and 0, 0? Well, let's look at 0, 0. So if my input is 0, 0, what's going to happen to that point if now my input is still 0, 0, right? So 0, if I plug in 0 for x, I get 0 out. So there's no change by translating, by multiplying the y output by 3. Okay, so 3 times y, because really what I'm doing is I'm taking whatever the x squared was and I'm multiplying that by 3. So what happens to 1, 1? Under this translation, let me rewrite this. Okay, so what happens to this translation? If I plug in 1 now, I get 1 squared is 1 times 3. The y value gets multiplied by 3. And now what happens to my negative 1? This time does the same thing happens. If I plug in negative 1 and squared, it becomes a positive 1 multiplied by 3. And I get 3 for the output. So the squeeze and stretch on this tells me that now when I plug in 1 for x, I'm not going to get 1 as an output, I'm going to get 3 as an output, which means the entire graph squeezes closer to the y-axis. Same thing on the other side. So an integer is going to squeeze, or a number greater than 1 is going to squeeze the graph, where a number less than 1, for example, y equals 1/3 x squared, what's going to happen when I put in 1, instead of getting a 1 out, I'm going to get 1/3. And so it would stretch the graph this way. So that's the effect of the squeeze and stretch. This is called, in our new terminology from our textbook, this is called a non-rigid transformation. So squeeze or stretch is a non-rigid transformation. and it's non-rigid because it changes the actual shape of the graph. Now, H and K don't change the shape of the graph in any way, so we call H and K rigid transformations, meaning they just slide the graph back and forth. So let's go and look at what would happen to our original graph under the influence. Let me do a little color coding here. 3 tells us to squeeze the graph. Okay, and then our examples, let me put this one over here. So we have that example, and I can erase extra stuff on these. Okay, so now we're looking at our graph has been squeezed or stretched. Now let's just move it back and forth. Well, this is a -2, which means I'm going to go forward 2 units because x is cattywampus. If it's negative, I go forward. So I'm going to pick up the whole graph. I'm going to move just the origin first. I'm going to pick up the whole graph and move it forward 2 units. And then H tells us to move up 8 units because, excuse me, K tells us to move up 8 units because K has no cattywampusness about it. So I'm going to go up 8 units. And so the new vertex point, or the new location for the vertex, is at 2, 8 rather than at 0, 0. Same thing's going to happen to all of the other points, every single other point, but if I just track 1 point on each arm, then I can lock that into position where I need it to be. So what happened to 1, 1? Well, 1, 1 moved forward 2 units, which takes me to 3 on the x-axis, and up 8 units. So from 1 up 8 units goes 9. And then -1, 1. -1 moves forward 2 units, which takes me to 1, and 9 is up 8 units from 1. So that's getting crowded in there, isn't it? -1, 9. These are called rigid transformations. Just a little bit of technology, a little bit of vocabulary for pre-calc compared to Algebra 2 of doing the same exact thing. All right, so one last bit of vocabulary. A rigid transformation is called a translation, which means that we just move the graph or translate the graph to another location on the Cartesian plane. And a non-rigid transformation is called a dilation, which I'm likely to call squeeze and stretch for eternity. But anytime I say or you read dilation, you should think in terms of squeezing or stretching, or your book says shrinking and enlarging the graph. Alrighty then, let's do some actual examples. We want to write an equation for this graph. And without grid lines, it's kind of hard to tell where it is, so I'm going to give us a lattice point. So we have a lattice point at 4, 3, and we have another one at x equals 1, y equals 2. All right, so this is clearly a root function. And we know it's an even root function because the dotted side does not exist. And so we know it's an even root function. We need to figure out if there's a translation or a dilation or both. Well, certainly there's a translation, and we can see that's super easy by just noticing that the origin went from being at 0, 0 to being at 0, 1. And we can keep going. The 1, 1 point migrated to 1, 2, and the point that would have been 2, 4 meaning you put in, excuse me, I've written that twice wrong. The point that would have been 4, 2, you put 4 into the radical and you get 2 out. Ah, now we know it's an actual square root. That was easy enough. That point went from being 4, 2 to being 4, 3. Okay, and what happened? The y value increased by 1 every step of the way. It didn't go anywhere on the x value. X values didn't change in any way. And it didn't actually change its squeeze or stretch, because when I put in 4, if I come down 1, I would have ended up at 2, and that definitely gives me the standard position for the root function. So our new equation then, and it's not f of x in this case, it's the g of x, or h of x, or q of x, or whatever. The g of x would be the square root of x, and all I did was go up and down, so it's actually the square root of x where the plus 1 is outside of the function, or outside of the initial function, the position of the x in the initial function. All right, let's do another one. So again, I have to give you lattice points because we don't have a graph to count them on. And it would be 1 and -4. And over here we have -1 and -4. So let's start with, clearly the parent function is the absolute value of x, right? Because that would look like this. That would have been this function, where -1, 1 is a point on the graph. The origin is obviously a point, and 1, 1 is another point. And we want to know what happened to make this switch. Well, the first thing we know, obviously, because it flipped over, is that this is part of the squeeze, stretch. Squeeze, stretch, and flip all happen. So our g of x, we know, is headed toward being a negative absolute. And I'm going to leave room just in case we have a translation on the inside. So it's going to be a negative absolute value of x. Now let's ask, did we go back and forth at all on the graph? And in fact we didn't. It just flipped over the edge. So we didn't go back and forth, so nothing is going to go in here inside of the initial function with the x. And then we asked, did we go up and down on the graph? And we did not, which means nothing is added here outside of the initial function. So a dilation is the last thing that could have happened. Let's see what we have. Well, 0, 0 went nowhere, right? It stayed at 0, 0. All right, that's not a lot of information. It's a little bit, but it's not a lot. 1, 1 went from 1, 1 to keeping the input of 1, but changing to -4. So I changed the x value, or excuse me, the y value, the output. So -1, 1, changed to, or migrated to, or flipped to, or anyway, whatever it translated to, -1, which stayed the same, and -4. So we can tell by quick inspection that all we did was multiply the y value by -4. So we just multiplied the output. So that means that our function is actually -4. Take the initial function, multiply the outputs by -4, and you get g of x equals -4 absolute x.